Identify quadratic relations. This is a very important thing to understand before we even get into quadratic functions, right? So first thing is how to identify a quadratic relation. Well, there are many ways to do it. One of them is looking at the graph. Well, here we have listed the three ways. One is looking at the graph, the second from the equation, third from table of values. From graph. Now, how do you identify from a graph whether a relation is a quadratic function or not? Or is it a quadratic relation or not, right? So, graph, we could plot like this. If it is a straight line, it is definitely not a quadratic function. It seems to be a line. It's a linear function, correct? So, from a graph, we can make out it's not a quadratic function. Second, if we have a graph like a parabola, let's say something like this, right? So quadratic functions normally will graph like a parabola. It may go upside down or it may just open upwards, right? Either way. But a graph, if you're looking for in this way, it could be a quadratic relation. Graph is not always a very sure way of doing it, but definitely it gives you a clue whether it is or it is not a quadratic function. So let me write this as a linear function, okay? And this seems to be quadratic. Correct? And if the graph is some other way, well, let me just draw some other way representing some other polynomial, it is definitely not a quadratic function, right? So for the time being, not quadratic. Okay, so we can say these are non-linear, this is linear, but amongst the non-linear graphs, the thing which is like a parabola seems to be a quadratic. So graph is a good way of figuring out whether it represents a quadratic relation or not, but it is definitely not a sure shot way of doing it. Sometimes we can have a scatter plot, right? So if you have a points like this somewhere, right? And if the pattern of the points is kind of a parabola, then you can say that a line of best fit could pass through it, which can be modeled using a parabola or a quadratic relation. So scatter plots can be seen, and if they are very close by, and if a line of best fit can be made in a form of a parabola, then that scatter plot can also represent a quadratic relation, correct? So graph, whether it's a line or a scatter plot, could represent a quadratic relation. Other way of representing quadratic relation is equation. Let's say we have an equation y equals to, let me write 2x plus 3. Now in that case, we know it's a linear line, y equals to this. And if we have something like y equals to, let's say x squared plus 5, and this particular thing is kind of coming down, let me just write minus because I'm writing under it. So this seems to be an equation of a quadratic relation, and this undoubtedly is a quadratic relation, okay? We could at times write in this fashion also, x squared plus 1, right? Y equals to x squared plus 1. Or even a quadratic relation equation could be x plus 1 times x plus 2 or something like that. So when you multiply two linear factors, you do get a degree 2 factor, which represents a quadratic function. But if the degree of your polynomial is more than 2, then it is not. For example, if we have 3x cubed plus 2x minus 1, here the degree is 3, so it cannot be a quadratic relation. Therefore, an equation in the form of ax squared plus bx plus c in general. So let me write a general equation for each here. It's a good time to write. So say an equation like y equals to mx plus b represents a line, right? But if we have y equals to ax squared plus bx plus c, it represents a quadratic function in a standard form. Okay. Now, sometimes you may get an equation which may look like a quadratic function. Let me give you one, right? For example, if I write x plus 1 times x minus 1 minus x squared. Now, does that represent a quadratic relation? Looking at it, we say y equals to this, the degree is 2 and this is also 2. It is, okay? But when you simplify it, what you get? X plus 1 times x minus 1 is x squared minus 1, and minus x squared will give us what? X squared minus x squared is 0, and you're left with just minus 1. So definitely this is not a quadratic function, right? So sometimes the equation may be misleading. You need to simplify it and then look at it very carefully before jumping to conclusions. Correct? Now, we come to the third thing, which is table of values. Table of values actually can definitely give you or suggest what kind of relation it is. So what do we mean by table of values? Normally, we have like x values and y values. Let's say x is the input and y is the output. And for each input, let's say we have 1, 2, 3, some inputs here, we have some particular output. Let's say the output is 5, 7, 9, 11. Let's say this is our output. So it is a relation, right? And it's also a function because we have unique values for each input. We have a unique output value. So it is a relation. How to find whether this relation is representing a linear function or a non-linear function? Well, the best way is to find finite differences, correct? So what are finite differences? As you know, if you have to check first these are your independent values. Independent values should be arranged so that you have a constant difference, and here the constant difference is 1 for independent values. Then you have to figure out the first difference. First difference is y2 minus y1. Think like this. Difference between consecutive independent variable values. Okay, so 7 minus 5 is how much? 2, correct? And similarly we do 9 minus 7, 2. 11 minus 9, 2. This is called first difference. I am writing like delta 1. So if first difference is constant, then it represents a line, a polynomial with degree 1. But in case we have a set of values where first difference is not constant, in that case it will not represent a linear line, but it could be some other non-linear function, correct? Now let me take this, a very simple example. I'm just assuming it to be x squared and see whether it really makes some sense or not. So if it is x squared, so I'm assuming that this is, I'm not assuming, I'm saying that it is a quadratic function. But we'll try to see whether the first difference is constant or the second, correct? Now here 1 square is 1, 2 square is 4, 3 square is 9. Now let me take more values. 4 square is 16. So if I find the first difference is 1 minus 0 as 1, 4 minus 1 is 3. This is 5 and this is 7, correct? 16 minus 9. So first difference is not really constant. How is the first difference related? It is like algebraic, like arithmetic progression, right? Increasing by a constant number, it's not constant itself. Well, let's find the second difference. So it is definitely not linear, right? Now let's find the second difference. 3 minus 1 is 2, 5 minus 3 is 2. So we get 2. So our second difference is constant. If the second difference is constant, then we are sure that the table of values represent a data which belongs to quadratic relations. Do you get it? That's how it is. It's the sure shot test for a quadratic relation. Well, for polynomials, we just continue this process. And let's say if fourth difference is constant, there's a polynomial of degree 4. If it is third difference constant, polynomial of degree 3. Okay. Now here is a small problem for you to try. So what we concluded from here, that how to identify quadratic relations. One way is to look at the graph, linear or parabolic. So if it is linear, it is line. If not, it's quadratic. Or if parabola, then quadratic. Now, then the second, we saw the equations, and sometimes the equations can be tricky, right? Now the third value was table of values. Here is a set of table of values for you. So let me just put this bit here like this. So we have a set of values in a table form, which I'm saying is the distance of stone from a cliff. Imagine you are standing on the top of a cliff, okay? And from there you throw a stone. At time t, when you just throw the stone, the distance from the top of the cliff is just 0, right? After every second, the distance increases. And these are your lengths after every second of time as the stone falls from the cliff. Do you see that? Now, you have to figure out whether this is linear, quadratic, or neither. How will you do it? Yes, you're right. Finite difference is the answer, correct? So, find the finite difference and figure out whether it is linear or quadratic or neither. Well, let me do it for you. 10 minus 0 is 10. 30 minus 10, 20. 60 minus 30, 30. 100 minus 60, 40. And 150 minus 100 is 50. So the first difference is actually not constant, but it's like an arithmetic series, right? It's going up by 10 each time. So of course, second difference will be a constant, and the difference is going to be 10, right? Because going up by 10 each time. So the second difference, 40 minus 30 is 10, and 50 minus 40 is 10. So the second difference is constant, and so this data belongs to quadratic relations, okay? So that's how it is. It's an easy way of finding out whether data given is representing quadratic relation or not, okay? I hope you appreciate and understand how to find whether the things given belong to quadratic relations or not, correct? Thank you.